All right, so we're back with week 5, and we talked about all of these topics. Let's do an example. This is out of Merriam Dynamics book, the Dynamics book that I used as an undergrad, although a much different edition. I used the second edition. We have a mass damper system. I'll work through here and saying that we see the weight is equal to 25 pounds. We got to remember we're going to turn that into a mass in order to use it. We also have this other information where we have K is equal to 160 pounds per foot. There's no dampers, so don't have to worry about that. At time equals 0, we have a velocity equal to 2 feet per second as it passes through the static equilibrium. So therefore, that is equal to 0, right? So the position at time 0 is equal to 0. So we want to find the static deflection. That's not a vibration problem. It's just maybe a simple thing where you go, okay, well, let me write it out. Okay, so if I was thinking, I was like, okay, well, stiffness is going to be equal to force over deflection. So that's going to be equal to the weight over the static deflection. So if we want the static deflection, we take the weight and divide it by the K. And you could even just use units if you wanted to here. So 25 pounds divided by 160 pounds per foot. And you end up with 0.1563 feet. And then you divide or multiply by 12, and you get 1.875 inches. Be smarter to report this in inches than in feet, just because we probably will be able to like visualize just something a little less than 2 inches, be 1 7/8 inch. All right, so that right there is A. Let me switch colors. We don't use orange enough, maybe because it's not very visual appearing. We want the natural frequency in both radians per second and in cycles per second. So we write out the square root of K over M. And here's a good exercise is to make sure we have the units out correctly. Take 160 pounds per foot and divide by the mass, but we are given the weight. So we'll go 25 pounds. And to get the mass from the weight, we divide by the acceleration of gravity, in this case 32.2 feet per second squared. And then I will cancel out the units here. These pounds cancel out the pounds, that feet cancel out the feet. So we're taking the square root of 1 over second squared. So we can be assured that we get the right set of units, which are going to be radians per second. 36. So we call that the circular natural frequency. But we also want to have the natural frequency in cycles per second, also known as hertz. And so we take, we have to multiply by, divide by 2 pi. If you're ever curious why, remember that you're taking 14, in this case 14.36 radians per second, and you're dividing it by 2 pi cycles, radians per cycle, I'm sorry, radians per cycle. And you can see that we get the radians out of there. We end up with cycles per second. So we end up with 2.285 cycles per second, which are defined by a hertz. We already made the joke about the hertz donut being mean to my little brother. So we got that one on the way. Now we have the system period. That's pretty easy. I'll write over to the left here. So we're doing a little carriage return to fit all this stuff in here. Here's the natural. Here's just 1 over Fn. So it's good to think in terms of seconds. A lot easier than the other results that we just got. We can visualize or imagine what this is nearly a half of a second for the thing to make a full cycle. And this, okay, so now they want an equation here. We want the displacement x is a function of time, where x is measured from the position of static, right? So maybe here's like where we're measuring it from. I'm not going to derive this. We already have done it. We know that the solution with initial conditions for a mass spring system, because it's so common, we can just write it out. That we have omega nt plus x naught times cosine. Right, so that's the full thing for the initial conditions. But things that we know are true here is that we're starting at x naught equals 0, and so we can put into the rest of the equation here, we can put in, we have 2 feet per second divided by omega n, which is going to be 14.36, and then take the sine of 14.36 t, and then just for wrapping it up, maybe I'll rewrite the whole thing. We'll say that x of t is equal to, okay, so the number is 0.1393 times the sine, hopefully I have enough room for 14.36 t. Boom. And so that answers that question. This next question is sort of a jerky one. The maximum velocity. Well, you could take the derivative of this guy right here, and then set the sine. Well, it was going to be set the cosine to 0, because that would make the cosine 1. But you would get the same thing. You should get the same thing right here. You should, because you're just going to multiply 14.36 times this value, which should get you 2. So the answer is just 2, all right? Because that's happening as it passes through the equilibrium point and is the maximum. I don't know why I started writing a box around it. We haven't done that yet. Okay, so we got this guy, and then the maximum acceleration. Okay, well, so in this case, maybe I would also put up in there that you would have, okay, so we would call this guy right there x. That's like our maximum x right here. So if anybody would ask what the maximum displacement is from the equilibrium position, that would be 0.1396 right there, right? Because that's going to be as far as the thing goes when it gets to when the stuff inside the sine gets to be like pi over 2. Right, so we're 90 degrees, so you get the sine is going to be equal to 1. That would be the maximum. So we know that we have, like, this is going to be, well, let me write down this way here. Max is equal to this right there. And we know that x dot max is equal to omega n times x, the maximum amplitude. So we have the maximum acceleration is going to be omega n squared, because we would take the derivative of this thing twice. So x max is going to be equal to 14.36 squared times 0.1393, and we get 28.72 feet per second squared, which is going to be the answer to this last one. I didn't change colors this time. One thing of note is that this thing is, so our note, less than G. 1G is 32.2. And it better be less than this, because it's got a spring that's keeping the thing from being in free fall. So, it's a couple interesting questions asked in class when we did this example about, like, well, could it ever be larger than 32.2? And I think it was Logan who asked, what if this spring, if in the process of lifting this spring up, it compressed the spring, so the spring actually was pushing down when the thing started from its peak. And I'm like, that's kind of an interesting type of thing. So I would like maybe to work through and try to see, well, this what if scenario, but I haven't yet. But is it definitely food for thought? All right, so we'll make another video as we go for the next example. This takes a lot of time.